Hello dear classmates. Today we are going to enter a new topic, delay test, which is important for advanced designs. We already learned a lot about stopgap fault testing for combinational circuits and for sequential circuit. Now we need to learn more full models about delay fault testing. Here is a motivating problem. You already know stopgap test very well, but this is not enough. Suppose that your manager asks you to generate a test pattern to validate an IC speed to make sure the path BEGJK timing is correct. So what are you going to do to generate a test pattern? So why am I learning this chapter? In this chapter, we will learn important delay fault models. We also will learn how to generate test patterns for delay faults and how to fault simulate these test patterns. Here is a quotation suitable for this chapter. It goes, "Delay always breeds danger, and to protect a great design is often to ruin it." This is what we are going to do in this chapter. We want to detect the delay faults in our design so we can make sure it can run at our specified speed. In this matrix, we have already learned many techniques for single stopgap fault testing, for combinational circuit, and for sequential circuit. In this chapter, we will learn delay fault testing for combinational circuit as well as sequential circuit. This is the outline of this chapter. First, we will give an introduction, and then we will introduce path delay fault and the transition delay fault in details. Then we will talk about how to apply delay test to sequential circuit. Then we will show 18PG model to generate test patterns. Then we will show experimental result followed by a discussion of delay test. Then we will conclude this chapter. So what is a delay test? Delay test is also known as delay fault testing. In delay test, we apply test patterns to detect delay faults. Intuitively, designer would use functional verification test patterns at system speed to detect delay faults. However, from a testing point of view, functional verification test patterns are not good enough to detect delay faults. To apply delay fault, we need to run the tester at high speed. So delay tests are also known as AC tests, as opposed to DC tests for stopgap fault. So why do we need delay tests? This is because some defects can change circuit timing, but not necessarily the circuit function. For example, random defects such as resistive open, resistive bridging defects, they may not change the function of the circuit, but it can increase the delay of the circuit. On the other hand, systematic defects such as crosstalk defect. A crosstalk defect can be caused by two wires which are too close to each other. Other defects such as process variation in the threshold voltage can also increase the delay of the circuit. To detect these defects, we need delay test. The second reason for delay test is that in modern designs, where speeds are getting faster and faster, small delay defects, or SDD, are becoming more and more significant. For example, a 100 picosecond small delay defect is only 1% for a 100 MHz clock period, which can be insignificant for old designs. However, for modern high-speed circuit where the clock period is 1 GHz, the same SDD is now 10% of the clock period. This can be a very significant defect. So we know that delay tests are getting more and more important for advanced IC designs. So how do we perform delay tests? To perform delay tests, we need two-pattern tests. This is different from stopgap faults, which only need one pattern test. In a two-pattern test, we have a pair of test patterns, or test vectors. In the first test vector V1, we initialize the circuit state. In the second vector V2, we launch a transition and we propagate the fault effect to the output. For the following example, if we want to test this OR gate, we can apply two test patterns. In V1, we apply 0, 0. In V2, we apply 0, 1. So we launch a rising transition at the input. At the output side, we observe vector 2 output at the specified timing t. If the output rises to logic 1 at time t, it passes the test. If the output cannot rise to logic 1 at time t, then it fails the test. So we need to control the timing t very carefully in delay test. If t is as fast as the system operation, then this delay test is called speed testing. Now we will introduce two popular delay fault models, path delay fault and transition delay fault, and we will compare their difference. In this chapter, we will introduce two popular delay fault models. The first one is path delay fault model, or PDF, which was proposed by Smith in 1985. A path delay fault is a path whose delay is larger than the clock period. The second delay fault model, transition delay fault model, or TDF, was proposed in 1986. The transition delay fault model is sometimes simply called transition fault model. A transition delay fault assumes that the path delay of all paths through the fault is larger than the clock period. In this square, we compare the difference between path delay fault and transition delay fault. The path delay 4 model assumes that the fault can be distributed along the faulty path, and it considers small delay faults. However, for transition delay fault, it assumes that the fault is lumped, and it only considers large delay. Please note that there are other delay fault models such as gate delay fault and segment delay fault. These four models are not covered in our lecture. This slide compares the difference between path delay fault and the transition delay fault. In this example, suppose that the clock period is 10 nanoseconds. For a good circuit, each gate delay is 2.0 nanoseconds. Suppose we apply this test pattern to test the circuit. For a good circuit, along the short path, we have 3 gates, so the short path delay is 6.0 nanoseconds. On the long path, we have 4 gates, so the long path delay is 8.0 nanoseconds. For the path delay fault model, we assume that the fault can be distributed along the path. So the first AND gate delay would be 3.0, the second one is 2.6, and the third one is 2.7, the last one is 2.9. If we test the circuit along the short path, the path delay accumulated is 8.3 nanoseconds, which is smaller than 10 nanoseconds, so the circuit can pass the test on this path. However, if we test the circuit along the long path, the accumulated path delay is 11.2 nanoseconds, which is larger than 10 nanoseconds, so it fails the test. As we can see, this is the assumption of a path delay fault model. On the other hand, the transition delay fault model assumes that the fault is large and lumped in this single faulty gate. For the other gates, the delays are still 2 nanoseconds. For this faulty gate, the delay is 9 nanoseconds. No matter we test the circuit along the short path or the long path, their delay are larger than 10 nanoseconds, so we can detect the fault. From this example, we can see the difference between these two fault models. This slide shows the number of faults for these two fault models. For path delay fault, there are 2 faults for each path. One is rising with an upward arrow and falling with a downward arrow. In this example, for the path B, E, G, J, K, we have 2 path delay faults. Please note that the number of paths in a circuit can be worst case exponential to the gate count. For transition delay fault, there are 2 faults for each circuit node. One is slow to rise, or STR. The other one is slow to fall, or STF. For example, for this NAND gate, we have 6 faults, which are A slow to rise, A slow to fall, B slow to rise, B slow to fall, C slow to rise and C slow to fall. Please note that number of transition delay fault is linear to the gate count. Now it's time for a quiz. For the given circuit, please count how many total path delay faults are there in this circuit. Also, question number 2, how many transition delay faults are there in this circuit? Please pause the video and do the quiz. Okay, now we are back to our lecture. For question number 1, first we need to count the number of paths. There are 1, 2, 3, 4, and 5. There are 5 paths. So there are 10 path delay faults in this circuit. Have you got it correctly? Now we count the number of transition delay faults. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes in the circuit. So we have 18 transition delay faults in this circuit. Have you got it correctly? Now we compare the path delay fault and the transition delay fault. In terms of the number of faults, PDF can be worst case exponential, so it's very difficult to test all the path delay fault exhaustively. We will need a given path list to generate the test patterns. On the other hand, transition delay fault can be linear to the circuit size, so it's comparatively easy to generate tests for TDF. In terms of fault size, path delay fault assume small delay fault that is distributed along the path, which is more realistic for real defects. However, transition delay fault assume the delay fault size are large and it's lumped. This may not be realistic for real circuits. In terms of silicon speed validation, we can use path delay fault test patterns for silicon speed validation. However, transition delay fault test patterns may not be useful to verify the silicon speed. Finally, in terms of ATPG, path delay fault ATPG is less mature, and the fault coverage is typically not very high. In comparison, transition delay fault ATPG is very mature because it's based on single stopgap fault ATPG, and the fault coverage is typically very high. In summary, PDF is very general in terms of definition, but it's difficult for ATPG. But TDF is relatively specific in terms of definition and is easier for ATPG. In summary, in this lecture, we have introduced path delay fault model and the transition delay fault model. Path delay fault assumed the fault can be distributed along the faulty path. However, the number of paths can be worst case exponential in number, so it's difficult for ATPG. By comparison, transition delay fault assume lump fault. The number of faults is linear to the circuit size, so it's easier for ATPG. Finally, we have an FFT for you. In this class, we mentioned that the number of paths can be worst case exponential to the number of gates in the circuit. Can you tell us why? Please give us an example where the worst case can happen. This is an interesting FFT for you to think about. Thank you.